So yeah, I wanted to go through some BGP use cases, just a couple of them. The whiteboard's there in case we want to do more kind of interactive Q&A afterwards, in that I don't think the presentation itself will take a full hour. I'm going to actually have a longer agenda, I think, for the summit in Seattle in September, and only have half an hour for that one. So I should speak slowly. So yeah, my name's Giles Heron. I work for Cisco. I'm really from a network operator background rather than a software developer. So I've been helping out a bit on some of the BGP stuff, mostly testing, been doing a bit of coding too, been, I guess, also working with the developers to kind of help them figure out, okay, what are the features we need, where should we be going with BGP and OpenDaylight. Done some work with NETCONF as well, but I guess ultimately, I've been kind of interested the last year or two particularly by what it is we can do with BGP once we have an API-driven sort of off-box platform for BGP. Really, I don't know how many people here have any kind of background in service provider networking using BGP, but generally with BGP, what we've tended to do is, the vendors have kind of given the operators what I'd always say is enough rope to hang themselves with. BGP has a ton of features, and all of us, I was going to say badge of dishonor, all of us have at least one BGP knob that exists that's our fault. So mine is the one where you don't do a next hop self when you're doing eBGP inbound, and that was because we were trying to get MPLS LSPs to cross multiple domains back in the day. So this must have been 16, 17 years ago. And of course, the problem is, the vendors create this new knob, and it's there forever. And I got caught by it about a year ago because I was configuring something, and I realized that my command completion wouldn't work as soon as I expected it to, because the knob that I'd added meant you had to go further before you could disambiguate. So it's a classic example. There are just too many features in BGP on vendors' boxes, and I'm saying that as a vendor, but I probably should take my Cisco hat off when I say that, because I guess there are those who like having these vast numbers of features. But what interests me is, okay, if you can take BGP, run it off-box, and have an off-box platform that advertises routes into BGP, perhaps you can do some of the clever stuff there and not have to put as many features on the boxes. And I think the way I always characterize it when thinking about OpenDaylight BGP and when talking about it is that in OpenDaylight, we have a BGP stack, and one question that comes up is, where did you get it from? And the answer is we wrote it from scratch. Two reasons for that. One is it's got to be written in Java because it runs in the JVM in OpenDaylight. The other is because, of course, everything's very much Yang-driven in OpenDaylight. So all of our interfaces in BGP are Yang modeled, and those are the APIs we have. But yeah, so we've written that stack, but then the question is, well, what do we use it for? Now, in the context of FDIO, for example, you might be using that as the control plane to a router. And what you might be doing is actually running BGP in OpenDaylight and then running NetConf down into Honeycomb so that you can set routes up. So that at that point, you are a router's control plane. But fundamentally, the way I think of it today is that OpenDaylight BGP is not there to be a router. It's there to interact with routers. So that's a sort of subtle difference in that routers fundamentally are concerned with building a fib. They run BGP and they have a RIB for one reason only. It's to build a fib. In OpenDaylight, it's so that we can interact with the control plane in the network, but also so we can build topologies. And of course, topologies are really the killer abstraction in OpenDaylight. So instead of looking at the network node by node, we can now see the picture of the whole network. To that end, I was going to go through two use cases today. The first one, I guess, is very topology-based. So it's how do you do traffic optimization using BGP-LS and PCEP? So this is really where the whole BGP-PCEP project came from in OpenDaylight. So learning routes with BGP-LS and then using PCEP to set up MPLS LSPs through the network. Slight twist on that today. I was playing with this last night, and I'm going to use segment routing. I don't know if anyone here in the room has come across segment routing, but it's the newest, shiniest thing in MPLS. Second use case was to look at DDoS mitigation. So that's one that comes up quite a bit also. So can you use BGP as a way of having, again, the off-box platform, advertising routes with BGP, and using those for DDoS mitigation? And there are a couple of different ways we can do that, and I'll demo one of them. So firstly, just an overview of the platform itself and how it hangs together. So you can see OpenDaylight here up in the top right corner. The BGP-SEP project has two separate plugins. So there's the BGP plugin and the PCEP plugin. As I mentioned, it's all OpenDaylight. Therefore, these plugins come with YANG models. So you interact with them through YANG models. So you have augments to the topology model. With BGP, you also have a RIB model. One interesting thing that we've been doing that came in Beryllium is implementing the OpenConfig BGP model. So I don't know if anyone here has been following the whole sort of politics around IETF and OpenConfig with YANG models. But at the Prague IETF hackathon last summer, we implemented the OpenConfig model in OpenDaylight. And for example, I mean, I'm at Cisco, and I can't speak for other vendors, but Cisco's now implemented that also in the router operating system, and now, great, you can effectively end up with the same model across multiple different entities, which should hopefully be helpful. I think the next step on that probably is going to be to use that model for a lot of operational data also. At the moment, I guess, in BGP, we're probably more focused on config. In terms of operational data, it's largely the routes themselves. So in terms of address families, as I said, BGP link state was where this came from, but we also implemented IPv4 and v6 unicast, IPv4 and IPv6 Flow-Spec. That's one of these little twists in the models, that in Lithium we had Flow-Spec, which was v4 Flow-Spec. In v6, we suddenly have v4 and v6 Flow-Specs. The names are different, so one thing to watch out for. We also have labeled unicast in Beryllium. In Boron, we're adding eVPN and IPVPN, so VPN address families. Now, if any of you, like me, unfortunately for a while I was the chair of the L2VPN Working Group in IETF, so I had the dubious pleasure of reviewing the eVPN draft before it went to RFC, and it's pretty massive. But again, as I said, we're not a router, we're interacting with them, so a lot of the complexity in that draft is really around how you interact with a FIB and what you do. It's actually relatively straightforward in OpenDaylight to add new address families, because really we're just talking about knowing what the AFIs and SAFIs are and being able to store them and advertise them. We're not having to get into the details of, for example, programming a line card with layer 2 routes or whatever. So it is easier for us in that respect. PCEP, so this is a protocol that came from the IETF a few years ago. There was this whole thing about how did we do into the main LSP. So back to my example of my BGP knob. Well, that was for LDP, and that seemed relatively straightforward. But for traffic engineering, the problem we always had was that in a traffic engineered network, a router only has a view of the link state topology of any directly attached areas. So if you want to go multi-domain, you need something that can see all those different domains. And so that's where PCEP came from. It kind of got resurrected a bit with SDN. And we'll come on to some reasons for that, because it didn't seem to have been going anywhere very much before that. And so with PCEP, you're talking to basically the edge routers to set up LSPs. Again, in Beryllium, in Lithium and Beryllium, we added support for various parts of segment routing there. So both for BGP-LS and for PCEP. There's still one gap. Someone was mailing me this morning saying, why can't I see the labels in the link state topology? And the answer is because we haven't yet updated the topology draft in IETF to put segment routing labels into the topology draft. So you'll see them in the RIB, but not in the topology. So there's always, I guess to that, we can say that there's always new stuff that we're doing. And so, as I said, in Boron, we've added eVPN and IPVPN. We've also added route refresh, and we've added, switching to American there, and BGP add paths. No doubt in Carbon, there'll be a bunch of other things that we add. So looking at the different types of routes. So the link state routes are the intra-domain routes. So fundamentally, this is stuff you're learning from ISAS or OSPF. So one of the routers then is advertising those routes over BGP-LS to the controller. And that's how we build our link state topology. Now, in some ways, that was a bit of an arbitrary decision to use BGP there. And that's why we've ended up with a BGP stack. It could have been that we'd have used something like NETCONF, YANG to do it instead. But it's great that we have the BGP stack now. Then you come on to V4 and V6 routes, which are fundamentally internet routes. So these are the routes we all know and love. The nice thing here, and I think that came in Lithium, was the ability to advertise routes as well as learning them. And I'll come on to that. And of course, that's critical to things like DDoS mitigation, because you've got to inject routes into the system. With labeled unicast, this is really how to do MPLS routes that are inter-domain where they've got labels attached to them. So that's kind of the cleaner way of doing, back to my sort of multi-domain LDP example, the way that the IETF ended up standardizing it really was to attach labels to the routes and actually use BGP between the two domains rather than LDP end-to-end. And Flow-Spec, so this is very much the BGP equivalent of OpenFlow. Now, the limitation is that because this is IP-centric, we don't have any layer 2 matches. But other than that, it's very much like OpenFlow. One of the benefits, I guess, is that we can leverage the whole BGP infrastructure. So we can send the routes out through the route reflectors. So instead of having to have a session to every switch, TCP connection and running OpenFlow over that, what you can do is you can say, OK, I'll send it out to the route reflectors, and I'll use route targets, so communities and things, to decide who gets which routes. So that seems like a cleaner way to do it. This picture is a picture of the OpenDaylight BGP rib structure. And what I'd say here is this is very much the same as any router, really. Fundamentally, what you have, so you can see here, this would be an external BGP neighbor over here, and then everything here is OpenDaylight. So you've got a connection to a BGP peer, and effectively within OpenDaylight, you get a notification that you've learned to route from that peer. Now, initially, that route will end up in the adjacent rib in, regardless of what was in that route. So any rubbish they advertise to us, it's still going to end up in there. So the first thing we do is we apply an import policy, and that generates the effective ribbon. So these are sort of the legal routes from that peer. In the case of OpenDaylight, I mean legal in that really the only policy we have is very much filtering out stuff it shouldn't advertise. So things with AS loops in them, that sort of thing. Now, again, longer term, we may implement more policy there, more programmable policy. But again, I think this speaks to this question again about how do we see ourselves in comparison to a traditional router running iOS or XR or Junos or whatever. Do we want to implement standard RPL for our route policy, or do we want to think about how it might be a little bit different in a controller? So one example of where we have a difference is that you'll see in OpenDaylight, you can spin up as many rib instances as you want, because again, there isn't a forwarding plane. So really, there is no concept of having this one rib that's tied to your forwarding plane chips. You can spin up as many ribs as you want. So maybe with policy, what it might come to is being a bit more flexible in how we combine these different chunks. So then you have the effective ribbon. So you'll have one of these for each of your peers. But of course, two different peers might advertise you the same route. And you've got to pick which one's best. So standard BGP best path selection then occurs in the lock rib writer, and that generates this lock rib. So BGP best path selection, again, anyone here who worked in an ISP environment any time in the last 20 years probably had the thing from the Cisco website on the side of its cube. I can see Gerhard smiling because I'm sure you did at some point. You'd have that thing on the side of your cube that had, was it 11 steps or something? I can't remember, but the different steps, so the tiebreakers effectively. So given that you have two different routes which are for the same prefix, well, which one do you pick? And so you go down through these different prefixes saying, OK, well, this one's got a higher weight, or it's got a higher local pref, and so on through the different tiebreakers until you find something different. Bizarrely, one of the tie breaks, I think, is the peer's IP address. And I seem to remember way back when I was working at a carrier, somebody in marketing came to us and said we really ought to make sure that our routers peered with the lowest IP address we could get our hands on, because that would help on the tiebreakers. So it gets a bit bizarre like that. And again, this is a classic example of, I suppose, what you'd call the SDN approach of saying, well, again, one of the things that customers come to us with sometimes is saying, OK, we know you guys are working with OpenDaylight. What we'd like to do is we'd like to effectively override best path selection. So normally, a classic example of this is that normally if you have a route, so say for network 10, of course that would be a private network, but let's just say somebody's advertising network 10, and they're advertising the whole of network 10. So that's a /8, it's 16 million addresses. and they're only one AS hop away from you. But somehow, through something more, several AS hops away, you've learned network 10 as a /9, so only 8 million addresses. So BGP best path selection would say that route is better because it's a longer prefix, and we're doing longest prefix match in IP routing. So are there tricks we can play where we override that? And so there may be things we can do like re-injecting dummy routes. We've done some stuff with BMP, which I probably won't have time to cover today, but it's another plugin. It's effectively derived from BGP. What BMP gives you, so it's the BGP monitoring protocol, and it's just become an RFC. What it gives you is the ability to access the adjacent ribbon and effective ribbon from your peers. So, for example, if OpenDaylight peers with a route reflector, instead of just seeing the best routes that the route reflector has chosen, it can see all the routes that were advertised to it. So imagine now if it's a peering router at an IXP, it'd be really interesting to see what all of your peers have advertised to you, rather than just seeing which routes you'd selected from those. So yeah, BMP, again, more around things like analytics, perhaps, than stuff we'd actually do in the control plane. But there are some control plane use cases, like I say, for things like overriding best path selection. The other thing we write to is an adjacent rib out. And again, we have one of these for each of our peers. Again, today, there's no great policy applied there. But again, that's something we should be looking at in future is how might we advertise different routes to different peers. Today, if you want to do that, you just have to spin up different rib instances. But there might be more flexible things we can do. So as I mentioned earlier, topologies to me are kind of the killer abstraction in SDN. In OpenDaylight, kind of everything ends up as a topology, as you're probably aware. Now, this is sort of a work in progress. So we had inventory and topology. Now sort of everything's moved into topology. Where we're moving towards is the new IETF topology drafts that actually separate kind of the node part of the topology, which is a little bit more like inventory, really, from the link part of the topology, which is real topology. So what you'll see at the moment is things like IPv4, IPv6, and PCEP. The topology's there, so they're all augments of the standard topology model that's in OpenDaylight. But in the case of those, you won't see any links in that topology. You'll just see nodes. In the case of link state, however, of course, because you're seeing a whole IGP area, and of course with multiple link state peers or a link state peer who's connecting to other domains, then you're going to find multiple of those areas. For each one of those, you'll have a graph that has links and nodes. So it's very much standard graph theory stuff. What's kind of interesting then is how you map stuff into topology. So I point to that again quickly. So what it comes down to, I suppose, is that you have to have an identifier for the nodes and links, and those are just opaque strings in the IETF topology model. What we do then is we take information that's pertinent to the protocol that we're running. So for example, in the link state case, you're going to take stuff like the router ID, like the AS number, like whether it's OSPF or ISIS that sent you this route, all that kind of stuff, and that will end up in the node IDs and the link IDs. What's sort of interesting with those is they're opaque strings, which doesn't really fit with the Yang kind of methodology. You can actually look at those strings, and they have like ampersands between the different fields in them. And you can see it'd be pretty easy to turn those back into some kind of more structured, JSON or XML or whatever, where you could actually see what the different fields meant. So that might, again, be something we need to look at, just to make people's life easier. So this case of using BGP-LS and PCEP for traffic engineering. So BGP-LS means that the controller can see the topology of the IGP. And all we need there is one router that speaks BGP-LS for each IGP area. Where that comes in interesting, I guess, is that you might find in a network of devices, for example, running iOS that doesn't support BGP-LS, you think, well, how do I get my topology? Well, you can get it by putting one virtual device in the network that does support BGP-LS, having that device peer with the other devices using OSPF or ISIS, and then have that device send you the routes. Having said that, of course, great to have a topology, but unless the nodes at the edges of the network support PCEP, you won't be able to set up LSPs across the network, at least using PCEP. As I say, PCEP, back to its original goal, the idea is that you can create inter-domain as well as intra-domain LSPs. What becomes interesting with SDN is this concept of stateful PCEP. So normally, with PCEP, a router could say, well, I want an LSP from here to here, and it'd be pretty much deterministic. The controller would say, well, here, have this path. And if it asked for another one, the controller would say, here, have this path, and it'll be the same path. So what about things like bandwidth allocation? What if you want to do, and again, this is the great benefit of having an off-box platform, is now, instead of looking at traffic engineering, where each node figures out the best LSPs for itself, you can now have something off the network that does a global optimization. But in order to do that, you have to be stateful, because you're going to have to track the bandwidth allocations through the network. And really where that becomes critical is with segment routing. Because if you do want to track bandwidth allocations, the problem is that while in RSVP-TE you can do that, because the LSPs get signaled through the network, and then the routers on the path can update the OSPF or ISIS-TE database with the bandwidths that are allocated. In segment routing, there are no LSPs. All there are is label stacks. So all the state has been taken out of the network and put at the edges, which is great because it's very much the IP way of doing things and more scalable, but it does mean that if we want to track bandwidth allocation, we have to do it in the controller. I think the last bullet was really just me saying, well, yes, PCEP is normally how we'd set these LSPs up, but for example, you could, having calculated what LSPs you wanted to build, you could use NETCONF YANG to just configure those label stacks at ingress, for example. It could be, in fact, this whole same sort of PCE methodology could be applied to a network that wasn't BGP-LS and PCEP at all. So you could apply it to an OpenFlow network. And again, one of the great things about the topology abstraction that we use in OpenDaylight is that it's not protocol specific. You take your topology, your base topology model, then, as I was mentioning earlier, you map identifiers from your protocol into that topology model. And then sort of if there's anything else left over, you use that as augments that topology model. But that does mean you can write an application that doesn't really care whether it's looking at an OpenFlow topology or a BGP-LS topology. So looking at topology, the network itself, as I say, it's OSPF or ISIS. If someone were to invent a third link state protocol, then I guess we could do that too. But it's pretty strict in terms of, with BGP-LS, the routes that you advertise have to have originated in the IGP. So you can't advertise any information that didn't start in the IGP. So for example, I think with ISIS you get node names, but with OSPF you don't, because that isn't carried around the IGP, if I remember right. And again, what we have is we have the standard topology model. We augment it to get a layer 3 topology model, but then we augment that again to get differences for OSPF and ISIS. And so one of the routes in the network, at least, will be the BGP-LS speaker. So on that router, again, with XR, there's one extra line of config in OSPF or ISIS, which is distribute BGP-LS. And then also you would need to enable the link state address family on that router and to OpenDaylight as its peer. And then what you'll end up with is this topology, which will be just a list of routers, which are called nodes in this, and a list of links. The links are unidirectional in the topology model. So I guess that comes back from the things like bandwidth allocations could be unidirectional. And so you may find, if you want to draw this, and the demo I'm going to show, it's drawing it in using a JavaScript drawing package that uses bidirectional links. So what you have to do is go through and combine your unidirectional links into one bidirectional one. The way you disambiguate multiple links between two routers is you have this concept of a termination point. So it's where the link attaches to the node. And again, in the case of link state topology, effectively the identifier for the termination point is the local IP address of that interface. And so if you go into the topology and look at network topology, app topology, example link state topology, it'll be there. Actually, we're probably OK for time, so why don't I give you a minute's rest from death by PowerPoint and actually show you that topology. Of course, it would help if I knew which screen I was on. Anyone see Postman? Probably a different environment. Sorry. Let's pick a node. Yeah, if you don't use Postman already, it's very much worth getting into. What I tend to do with it is I have all these collections and I put them on GitHub. So all these collections of things like PCEP, BGP, NETCONF, whatever, different REST commands that you can issue through Postman. What I then do is I keep environments so that if I go now to the environment I just created. So now, for example, I can just find my PCEP. Let's go to PCEP. Actually, we're on BGP-LS, weren't we? So let's go to BGP-LS. This is the first point where everything could go horribly wrong. No, it doesn't. Good. So this is a link state topology that's running in dCloud. So dCloud is an infrastructure we have at Cisco, and if you have, as long as you have a Cisco account, you can use it, and it's quite cute because you can spin up various demos. So the demo I've got here is 8 virtual routers and a virtual node running OpenDaylight. But there is a VPN hooked into this as well. So you could run OpenDaylight locally if you wanted to do some coding and play around with OpenDaylight locally. You can write your code and then connect to the dCloud infrastructure. And so here you can see, for example, the list of links. And as I mentioned, the link ID, it's saying ISIS level 2, type is a link, and there's that ampersand separating the different entries. You can kind of see that this could just be, it's ISIS, and there's a type, and that's kind of the key, and then the value would be link, et cetera, et cetera. So it might be there's some better stuff we could do with it. So that was link state topology. Just because I'm about to come onto PCEP, I'll show you the PCEP topology. And in this case, what we see is just nodes. As I mentioned, there are no links. So if I contract that list of nodes, there are no links there. And what you'll see for each node is just information about its PCEP status. If there are any LSPs, those LSPs will appear in there. So we'll come back to that with a demo probably. Right, so what you have, the nodes are basically the edge routers that run PCEP. So in PCE, those are called PCCs, Path Computation Clients. So what you'll do in your configuration, whether it's XR or Junos or whatever, is you'll go in and you'll configure your sort of MPLS traffic engineering and say, well, I want to use PCE. This is my PCE node. And then there are a couple of different ways to set up LSPs that I'll show you. And so the topology itself, which I just showed you, is available here. In terms of setting up LSPs, what happens is that the topology model, there's an augment the topology model for PCEP. And amongst the things it's augmented with are these 3 RPCs. There's one to add an LSP, one to update an LSP, and one to remove an LSP. So there are then 2 ways to do LSPs. One is where the controller completely owns the LSP. The controller pushes them down onto the router. In that case, you need all 3 of these RPCs. When you do the add LSP, you need to put the whole path in to get the LSP added correctly, but you can then update it, and eventually you can remove it. And that's what my demo will use. The other model is delegation, where the LSP is created on the router, and the router then says to the PCE, please, can you take care of path selection for me? And the normal way to set that up, so this is setting this up again in XR in this case, and you can see you have a signaled name, and that's how the controller will identify this LSP. And we've said we want to delegate it to PCE. Now, you can even do mixtures. So you could say I've got these 4 different path options, and some of them are ones that I set up manually, and another one's one that I've delegated to PCE, and yet another one's LDP, for example. So you've got that flexibility. In this case, you don't need the add or remove LSP because they're being added and removed through the CLI or through NETCONF. But you do, of course, need the update LSP to bring the LSP up. And on the update LSP, what you'll give is a complete path from source to destination. So you'll effectively give it an ERO, explicit root object, encoded in Yang, of course, or Yang modeled, so it'll be JSON or XML, and you'll have each individual hop on the path. So, time for a demo. What I have here, let's go back to the screen. Sorry, I find it kind of weird when my external screen is is underneath, not on top. That's dcloud. That's OpenDaylight. Good. Right. Ha. I didn't quite go far enough, sorry. There we are. So this is the network that's running in the cloud. We have, I think, 4 different cloud instances. This one's running in London. But although it's running in London, you know, we're an American company, let's admit it. And so the only map we seem to have is a map of the US. And our demos invariably are either just, I know, sue me. I've got to get that fixed, haven't I? Because, you know, with that, we're in Berlin. For goodness sakes, there should be a Berlin node. And also, I don't know, again, anyone here who worked in the European SP market back in the late 90s, as I did, it was all very kind of, everybody had that ring that went sort of London, Brussels, Amsterdam, Düsseldorf, Frankfurt, Paris, back to London, and then the other ring that connected in Düsseldorf and Frankfurt and went around Germany. So we could at least draw that on this. And yeah, so these are all just virtual routers, you know, running as VMs in the cloud. There's an ODL that's talking to them. So let's set up an LSP. So should we switch my phone off, shouldn't I? So let's do the endpoint selector first. So I have no idea. I suspect there's a router in Kansas City because it's the middle of the country, not because anyone actually lives there or anything. Sorry if I've just insulted anyone here from Kansas City. So what will happen here is we can either choose IGP metric or hops. And in each case, it'll give us the different options. So we're running a modified version of Dijkstra here that a colleague of ours called Nicholas wrote. So it's called Nijkstra because, you know. And what's actually happening, I'm determined to use the whiteboard. So what you're seeing in reality is you've got an OpenDaylight instance that's talking northbound on port 8181. In there, you've got a BGP plugin and you've got a PCEP plugin. I hope this is sort of visible. I'm probably not drawing it big enough. So again, BGP only needs one connection on port 179 to the route reflector, which I think in this case is San Jose. PCEP, what you'll have is each router will connect in. So PCEP runs that way around. And that'll be on port 4189 on the controller. What we then have is the Pathman application. In fact, in this case, it's Pathman SR because we're using segment routing. So that's connecting on port 8181 to OpenDaylight. And Pathman is actually a bunch of Python code running in a container. What we then have is my web browser. And what we have here is some JavaScript running in the browser. And that's talking, I think, on port, in fact, you can see it up there, it's port 9080. And it's using this topology library called Next. There's also a version of this that uses Deluxe. And I think for that one, it runs on port 8020 by default. So the functions that this Pathman code has, one is, as I mentioned earlier, this topology model thing, that it says, OK, I've got this topology model where links are unidirectional, where the node IDs are these funky strings. What I want to do is compress it down so my links are unidirectional, my node IDs are the node names. You know, it's all much easier to deal with. So it does that and then presents that to the JavaScript, and that's what the next code is drawing there. It also exposes some RPCs northbound for things like creating LSPs and for exposing what these different possible paths are. And it's all open source, so it's probably a good example you can look at if you want to start doing, I suppose it's the 21st century version of 3-tier client server, isn't it? When you think about it, you've kind of got this JavaScript stuff in your browser, you've got this blob of Python, and then talking to OpenDaylight. Okay, so let's pick one, more or less at random. We'll give it a name. You'll guess I'm going to set up 2 LSPs, given by the name I gave the first one. I'm actually clicking on it. Oh, I didn't actually pick it, sorry. I wanted that one, didn't I? Sort of around the houses a bit. Yep, that's there. So let's do another one, just for fun of it. Start at KCY again. Maybe we'll go to San Diego, but this time we'll do a manual. Oh, actually, we do it that way. Yeah, manual path. So we start there. And with this one, yeah, you literally just select the nodes you want to go to. So we can go completely around the houses. Don't know why we'd do that. Call it bar. Yep. So now we have 2 LSPs in the network. And if we go to the router, it's down there, isn't it? Let's get a... In fact, at first I could show you on Postman. That's probably easy enough. So this is the PCEP topology. So what we should find is when we go to KCY, once we can find KCY, did I send that again? Can't remember which one it is. Oh, there you go. So this is Kansas City, and you can see we've now got a couple of LSPs. So there's foo, and you can see this is the path. And you can see the ERO has been encoded using this Yang model where we've effectively each hop we're putting its IP address and we're saying it's a nodal segment, and that's the label we're using. So if any of you here have come across segment routing, there are basically 2 kinds of segments you can have. One is a nodal segment, which is basically unique within the domain, so it's almost like a global label, and it's advertised through ISIS or OSPF, so there's no signaling required. The other thing you can have is an adjacency segment, which is basically saying, this is one of my interfaces. So you could use those in your path instead, but it's just easier here to use the nodal segments. So if you then go to the router itself, so let's, I think this is Kansas City. Yeah. Yeah, so you can see foo there, and you can now see its path, and you can see that it's saying PCE controlled. So those paths are being set by the PCE. And then, of course, in the demo, I could just go in and delete them, whatever. But really, what that I guess what that demo is showing is, ultimately, it's this architecture here, and really, Pathman is acting as that PCE on top of the network, using RESTconf as its interface into OpenDaylight to make these decisions. But equally, that could be a full-on commercial PCE like Cisco's Way product, or there are obviously other ones out there in the market. Or in fact, you could write a PCE as a component inside OpenDaylight if you wanted, and then use the binding aware Java APIs or the binding independent Java APIs instead of using RESTconf. So I think there was some work done on that. But it'd be interesting to see if we could get, probably not, again, within OpenDaylight, we may not want to build sort of the world's biggest, highest-end PCE, but it might be nice to have some kind of lightweight PCE inside OpenDaylight, particularly if we could make it multi-protocol, so that we could use the same PCE for BGP-LS as we use for OpenFlow, that kind of stuff. That might be quite nice. So let's have another use case, and that's DDoS mitigation. So the first thing here is we're going to need to advertise routes. Now, the tricky thing in OpenDaylight is the RIB that we have is operational data. It's not config data. So we need to find a way to inject routes into the RIB. The way we do that is through this application peer. And the application RIB is effectively just the config version of the BGP RIB. So it'll be in the config tree, not the operational tree. It peers, in inverted commas, with the main BGP instance on the router. But that's kind of a special sort of peering because it's all internal. You actually do give the application peer a RIB ID, but again, that's only part of this long tiebreaker list in BGP best path selection, which shouldn't really apply. But again, this is where my view is that we perhaps want to be a little bit more flexible. Perhaps we need a way that we can config routes that go straight to an adjacent RIB out that don't go through our own locked RIB, because there are many use cases, and this is probably one of them, where we really don't care about best path selection. We don't care about learning routes. All we want to do is inject routes, so we don't need all that machinery. The peer is kind of like an iBGP peer, but the difference is that routes are effectively reflected to other iBGP peers, albeit without the cluster IDs, et cetera. That's something we had to change about 9 months ago, because we originally did act exactly like an iBGP peer, which meant it wasn't very useful when you were doing iBGP peerings. So we can do that with v4 or v6, but we can also do it with Flow-Spec. As I mentioned, very like OpenFlow, but effectively, we've got these matches, which are all, as you see, IP-based, not layer 2. And then the actions are then encoded as BGP communities, and the actions can be the usual sort of rate limiting, traffic sampling, redirection, et cetera. So really, when it comes to DDoS mitigation, there's probably 2 different approaches. The one I'll demo, because I only had time to set this up, is because I wanted to use a very simple IPv4. If you know that there's somebody attacking you, so for example, there's somebody out here attacking us, and we know their IP address, and we want to block all traffic from this bad actor, then all we need to do is, if we've turned on unicast reverse path forwarding, now what that says on the routers, and this is something we've had for a while, it says on the router, well, if I get a packet that's apparently from this address, but it's arriving on the wrong interface, I'll throw it away. Now, in this case, of course, the packet is arriving on the right interface because the guy's bad. It's not that he's in the wrong place, it's that he's bad. But we can still block it. And the way we can block it is if we advertise a more specific route than the one we normally learn from BGP, and if we give that route a next hop that we know will end up in the bit bucket, then his traffic will get dropped. So what we do on each router is we put in a static route for 192.0.0.2.1, which is, I guess by convention, the address people use for this sort of stuff. And we tie that to null on the router. Then what happens is when we see this traffic that we don't much like, what we do is we inject this route into BGP for that /32 with the next hop that's going to get pointed at null 0. And that will block the traffic. The question then, of course, becomes, how do we know that this is happening? I guess, again, this is where in the SDN world, the way I tend to think about this always is that you kind of have this loop where you learn something. So if this is your network here, and this is your SDN layer, you sort of have this loop where you learn something, and then you act. I guess pilots would call this the OODA loop or something, wouldn't they? But there's some kind of you've got to learn something's going on in the network, and then having learned that, you take some kind of action. And what we typically see is different protocols get used for those 2 different things. So, back to BGP-LS and PCEP, BGP-LS is how we learn topology, and then PCEP is how we act and push topology into the network. In this case, we're using BGP here as our action, but the question then becomes, well, what is it we're using to learn that this is going on? So there could be a range of things, I guess. It might be that you have things running on hosts that you're talking to that say this host is under attack. It might be that you're looking at net flow statistics. It could be a range of different things. And so I'm only really showing this sort of action side of it. I'm ignoring the other part. But this applies to so many things. Like I mentioned earlier, this sort of overriding best path selection. If you're doing that, you might well be using BMP to learn what's going on, and then using BGP as your way of taking action. And there are other cases. So I've looked at other cases with, think of examples. Things like DNS, where you might be seeing what's going on, and then you might be programming actions as a result. And I think that's something that we may need to think about more, is what are the things we're using to learn what's going on? It seems like the big thing at the moment from the router side of the house is telemetry. So maybe that's where we need better hooks in telemetry to see what's going on. So, oh yes, demo. Right. So here is my infrastructure, which obviously has timed itself out because I've not been using it. So I can ping. I am IPv4. This is the guy I'm attacking. We need the address of the bad actor. Yeah, so that's all worked. And if we look at, for example, the guy in the middle, what we can see, sorry. Well, we'll do it this way. So those routes aren't there, the specifics, but if you look at the /24s, whoops, you should see, yes, we're learning that from the guy on the left, and we're learning this route from the guy on the right. So that fits the diagram I had there. So if we want to block this bad actor, I guess what we need to do is go to my other environment. So right, so you can see I'm injecting a route that's a specific, a /32 for this guy, and that's my next hop. So let's put that one in. Okay, it's saying okay, that's usually a good sign. Probably if we look at the app routes, you'll see the route there, yeah. So you can now see that. And as I mentioned, that's configuration data, and you can see a config there. I use macros all the way through my postman to hide these enormous URLs. So now if we go back to the routers, what you should see is, see that will still be the same, but if we now go back and look for the /32, what we can now see is that we've learned that route that's pointing at 192.168.192.0.2.1, and if we do a show route on that, you'll see that that's statically connected to null 0. So now if I go back and do that ping, and then you can see that's now blocked. So what's happening is the packets are getting to that second node, and because the second node because on that interface facing the first node we have this unicast RPF, when the packet arrives, it'll say that source address shouldn't have come from this interface. It should have come from null 0, so it'll drop the packet. Got to find where I put PowerPoint. In fact, that's pretty much it. So I guess, probably the best thing to might be we've got, I don't know, Phil, we've got 10, 15 minutes. We've certainly plenty of time for Q&A, but equally, if anyone needs to run out and head to lunch early, that's fine too. As I say, I very much focus just on these two use cases, but feel free to ask questions that have anything whatsoever to do with BGP and PCEP, and I'll sort of do my best to answer them. Stunned silence. There's actually another example of, I guess, what I mean about not being a router and wanting to interact with them instead. Another example we had of that was if you think in terms of IPv4 and IPv6, initially there were constraints in the code to make sure that you couldn't learn an IPv4 route with an IPv6 next hop and vice versa. And then we were like, most routers would have that because it sort of makes sense if you're a router. But actually that's sort of dumb when you think about it from an ODL point of view, because we might want to be able to do that. So we just took the constraints out. So now you can have an IPv6 route with an IPv4 next hop, or vice versa. And again, where that may be interesting is in terms of using the controller to build virtual overlay platforms. So if we want to have an overlay, for example, carrying v4 as a service over v6, we now have another way of controlling that. So it would be previously, we'd probably have to use something like Lisp as the control plane, which is fine, we have Lisp in OpenDaylight. But why not, for example, use the Lisp encapsulation, use something like FDIO as our forwarding plane, and then use BGP to advertise the routes. And advertise those routes, even though the network is v6, advertise v4 routes using BGP. So I think the way I'd see it is we always need to think in terms of, what is it we're trying to do here, and from an application perspective or a use case perspective, and then figure out how do we combine these different protocols in that kind of loop I showed earlier to achieve that. Another thing that I should probably mention briefly is clustering. So although clustering's there in OpenDaylight, we don't yet really have a clustering story for BGP. Personally, however, I'm not convinced we need one. Because when you think about it, a lot of the internet protocols were really designed with the assumption that routers were fragile things. And I guess, again, in my service provider background, we never, I shouldn't say this working for Cisco, but we never put those second root processors in. Because, what's the point? We had 2 core routers. If one of them fell over, the other one would take over. And actually, often, the complexity that you add handling these use cases can cause more problems. So I sort of think with clustering, for example, what I sometimes do then is just configure my routers with, say I have an ODL cluster, I'll just configure the routers so that they have a peer group, which is effectively the 3 nodes in the ODL cluster. That way, all 3 nodes in the cluster get advertised exactly the same routes. So if you have an application running where there's something that has to be on the shard leader, it shouldn't really matter because all 3 of the nodes are going to have the same routes. So it doesn't matter if that app moves around. So again, I think sometimes we need to perhaps take this sort of system-wide view of it. And so not focus totally on, say, BGP or on a clustering infrastructure, but think, what's the application we're trying to do? And what is it we need to do in the controller, in the system to achieve that? I mean, does anyone here actually use the BGP plugin at all? As one, that's good. What do you use it for?
Well, we try to use it for loading VPN addresses that dynamic allocated to bring services to instances.
Right.
The problem is obviously VPN labels get dynamic allocated, so you have to statically route MPLS labels to work. So.
Yeah, that's a really interesting one, actually. The whole, this whole issue of VPNs and SDN, because I kind of think that to some extent, what we'll see is segment routing as the protocol of choice in the core for the transport labels, particularly when you have something like OpenDaylight. But I tend to think that with the kind of VPN labels, we may have a mixture where in the sort of access networks we just assign them statically. Now in the core you probably do still want BGP. So you may find where service providers have a classic sort of flower petal architecture with a core and bits around the edge, that they have pseudowires at the edge where they're statically assigning the labels. And then in the core they use BGP. But at least once with Boron we have the EVPN and IPVPN address families, we'll at least be able to interact with that. There was something I was setting up the other day and it came to that. I was thinking, why doesn't this work? And I was remembering, oh yeah, of course, I need to advertise the service label. And so in the end, yes, the way to do it was to say, well, we'll put the controller in charge of assigning these labels. So we'll take that issue away from the router at the edge and say the controller's in charge, it'll take care of them. Some of that then speaks to how you do your kind of decomposition from a sort of high-level service model that says, I want to configure this MEF line from one side of the network to the other, right down to the bottom, which is I'm configuring a router, and there's a sort of sub-abstraction in the middle where you're saying, I know it's an MPLS pseudowire, and I want to assign the labels, and I need to track all my labels and stuff. And so I guess I see that as the function, perhaps, of the controller to present that kind of more neutral interface below which it tracks all those identifiers and then talks to the network. And then you have an orchestrator on top that doesn't have to worry about those annoying details, because if I'm an orchestrator, I don't really care about an MPLS label. It's not top of my list of concerns.
So one of the main issues we have is literally the existing networks, because the people doing NFV and future services don't operate the network, and the networks don't want to change to anything that's not dynamic.
Yes.
They spent 15 years building that network now, and they trust it. Yeah. It's really how we get the two to interoperate together, and it's whether we can use OpenDaylight to do that translation between dynamically allocated VPN labels to services.
Yeah, that would be interesting, and yeah, whether you can use it at the sort of, particularly if you've got the WAN is sort of traditional inverted commas, then your data center's the new piece, whether you can have the controller doing that kind of interaction between the two. I'm personally, I like that approach rather than having a router do this translation from one to the other.
Very good. Thank you very much, Giles.
Yeah, no worries.